Our objective is to be able to select the best scale specification to fit a particular object onto a piece of drawing paper or an available area on a drawing. So the scales that we have available are to choose either the architect, engineers, or metric. The item itself is the real life thing, and then the drawing space is what we have available on our physical paper or what we have available in a particular drawing program. Our first example here is asking us to select an engineering scale specification, and what we're doing is we're fitting a view of a tugboat, which implied is 67 feet tall by 248 feet wide. The particular available space that we have is 18 inches by 22 inches. So what we're going to do is match up our proportions. So we'll try to fit the short side with the short side and the long side with the long side. We've got 18 inches available on the short side, the 67 feet height of the tugboat. The question is, we're trying to match those exactly. Now, it's unlikely we're going to get them exactly, but what we're going to do is calculate the ratio to figure out what is the target ratio that we need to make the adjustment fit. Adjusting from feet to inches and then dividing both sides by the smaller value, we get a ratio of 1 to 44.67. So to fit the 67 feet into the 18 inches, we need a reduction of 44.7 times the original size to fit into the paper. We need to check the other dimension. So how does the 22-inch available paper space accommodate the 248 feet of the real-life tugboat? So similarly, we go through and figure out the ratio. And now we have a ratio of 1 to 44.7 and a ratio of 1 to 135.28. Which one is the limiting case? The limiting case in this situation is going to be the larger reduction. So the larger reduction is the limiting case, because if we don't do enough reduction, the item's not going to fit. So our 1 to 135.28 is the target ratio. Here, the next step is to try some possible engineer scales that one might think of. You might think of 1 inch equals 10 feet. You might think of 1 inch equals 100 feet. In this case, we're going to try with 1 inch equals 20 feet. Total guess, we're going to use it to evaluate how close our guess is. With a try of 1 inch equals 20 feet, convert that to a ratio, and the ratio is 1 to 240. That ratio is enough reduction compared to our target ratio. We cannot do less reduction than the target ratio. The question is, can we do better? How about trying 1 inch equals 10 feet? Compute the ratio. The ratio is 1 to 120. That is not enough reduction, because 1 to 120 is less reduction than the target ratio. Maybe someone thinks of trying 1 inch equals 12 feet. 1 inch equals 12 feet, compute the ratio. It's a ratio of 1 to 144. That's closer than our previous attempt, but the problem is a scale specification of 1 inch equals 12 feet is not a valid engineer scale because the engineer scale must match 10, 20, 30, 40, 50, 60. So the significant digit is not available on the engineer scale. So that is not appropriate. Optionally, someone might think to set a specification of 1 inch equals 4 yards. Understanding that 3 feet per yard, we do a little conversion of 12 feet. 12 feet is equivalent to 4 yards. So the ratio of 1 inch equals 4 yards is a ratio of 1 to 144, which is very close to our target ratio. Listing this as optional because yes, 1 inch equals 4 yards. The 4 matches an appropriate significant digit on the engineer scale. So we would use the 40 scale in this case. But our original dimensions were in feet. There may be a preference of using feet rather than using yards. In our course, this ratio of 1 inch equals 4 yards has no problems. So that would be acceptable. However, the preference in our situation here would be to use feet, since that's the original question given in feet. So in this example, we have the fact that for an engineer scale to do the appropriate selection, we would use 1 inch equals 20 feet, and that would make it so that someone could draw the tugboat in the available drawing space. Example 2. Select an architect scale to fit a tennis court overhead view, 36 feet by 78 feet, into an available paper space of 7 inches by 16 inches. Go ahead and pause the video and please determine the target ratios along each direction. Computing the target ratios, we've got 1 to 61.7 and 1 to 58.5 along each dimension, thus remembering that the larger reduction is the target. So we will use 61.72 for the target. Having the target ratio, pause the video and try to find the best architect scale to match that ratio. Here are some attempts that may have been tried. 1/2 inch equals a foot with a ratio of 1 to 24. 3/16 inch equals 1 foot with a ratio of 1 to 64. And 1/4 inch equals 1 foot, a ratio of 1 to 48. The closest ratio is the 1 to 64, and it is enough reduction. So 1 to 48 is too low of a reduction. 1 to 64 is the closest we can get using an architect scale. Thus, to do the desired task, the architect scale we would want to use is 3/16 of an inch equals 1 foot. Example 3, a metric scale, trying to fit soccer field into an available paper space. Pause the video and please compute the ratios for each dimension. Computing the ratios, you can verify the shown ratios along each dimension. In this case, the limiting target ratio is going to be 1 to 328.6. With that target ratio, now we think about what is the best metric scale to use to match that target ratio. Pause the video and give that a try. Now for the metric scale, we have 1 millimeter equals some distance. And since we have to match the target ratio reduction but not go below it, it's a matter of taking the 328 and increasing that until we hit some ratio pattern that's available on the metric scale. In this case, it's increasing the 328 to 400, which is setting the ratio to 1 millimeter equals 400 millimeters. We have our choice of units, and since the soccer field was given in meters, the equivalent expression of that scale specification is 1 millimeter equals 0.4 meters, since there's 1,000 millimeters in a meter. Our answer to this example then would be to use a metric scale of 1 millimeter equals 0.4 meters. In our final example here, select the best metric scale to draw this fastening clip, which is a relatively small clip, 5.8 millimeters by 7.4 millimeters in overall dimensions. And our paper space is a large available paper space, 26 centimeters by 29 centimeters. Pause the video and compute the target ratios. In this example, we do have some options on how we want to view the ratio. Computing the ratio by dividing by the smaller side of this paper and physical side, we get ratios of 44.83 to 1 and 39.189 to 1. When the paper side of the ratio is larger than the physical side, the indication here is that we have a magnification that's capable. When we have a magnification that's capable, the limiting case is going to be to select the smaller magnification. If the magnification is too big, it's going to be not going to fit in the space. Now, the viewpoint that I will recommend here is that the metric scale is always 1 millimeter equals blank. So rather than dividing by the smaller value, what we want to always do is divide by the paper side. So the ratio of 1 to 0.02231 for the left column is determined by dividing both sides of that paper and physical column by 260 millimeters. The right-hand column, trying to fit 7.4 millimeters into the 29 centimeters on the paper, we get a target ratio of 1 to 0.02552. The value of this is that the target ratio is still always the larger physical side number. So we notice that 1 ratio to 0.02552 is larger when we look at the physical side than 0.02231. It's the same logic where the larger reduction is what's required. However, when the reduction goes below 1, we're actually doing a magnification. With this target ratio of 0.02552, what we have is the ability now to set the metric scale of 1 millimeter equals 0.030 millimeters. And we have to go up because that's our sequence for the system of looking at the physical side and making it a larger, quote unquote, reduction. One might argue that we do have the 250 available on the metric scale. So isn't 1 millimeter equals 0.025 millimeters actually make that ratio go down? Wouldn't that be better? And in all arguments, yeah, if we're that close, it might be the better choice. But in terms of our numbers, if we do 1 millimeter equals 0.025 millimeters as the scale specification, it's not going to fit in this 26 centimeter by 29 centimeter available space. It'll be very close, but it's not going to fit. So with our context of our class, that is not going to work. We need to select a metric scale of 1 millimeter equals 0.030 millimeters, and we'll have some extra margin in the drawing space. One final note is to observe and appreciate that ratios are used to compare scale specifications. A ratio of 1 to 148 or 1 to 50,000 or etc. Those are our comparison targets. The scale specification must include units so that we know which unit system we're in, either metric or English. Also, in terms of the format of the scale specification, we know which system, either architectural or engineer scale, we are using.